All right, section 5.1, we're going to take a look at integers. In fact, all of chapter 5 is integers. So 5.1 is going to be addition and subtraction. 5.2 is multiplication and division. So as you're taking a look at the options you have for your sections that you're going to present on and so forth, you don't necessarily know what's in 5.2 yet. I'd encourage you to look at that and see if that's something that looks interesting to you to do. But you'll get a little bit of a feel for what it looks like from what we do in 5.1 as well. All right, let's do the leading idea first. Adding and subtracting integers helps us understand movement, balance, and change, concepts reflecting the order and purpose woven into God's creation. These operations teach us how to combine opposites and find equilibrium, reminding us of the harmony within complexity. Integrating faith with the study of integers encourages a thoughtful teaching approach, inspiring us to help learners discover how mathematics reveals deeper truths about relationships, balance, and growth in numbers and life. Let's pray. Dear Heavenly Father, I thank you for the opportunity for us to encounter our last chapter of material today. I pray that as we work through this material and we work through details on how to explain this material to others, that you would be in our discourse, help each of us to be able to ask good questions and answer effectively. Be with us today, we pray. Amen. Starters. What is integers? Well, we've encountered some of them before. Your book does use the letter I for integers. You should know that's not typical. Integers usually uses the letter Z, and it looks like this. I mention it because if you see it somewhere else, I don't want you to be surprised and say, why did they use a Z? Your book's actually the one that's weird. But we've got your book to work with. Half of the integers we've already worked with. We've been working with them all semester. They're called whole numbers. So 0, 1, 2, 3, and so on. What we've actually got now is their additive inverses, the opposite of them. So we have a -1 and a -2 and a -3 and so on. So our integers look like that. In particular, we've learned set notation, and we can put them inside of those set brackets. Okay, y'all have seen these before, right? They typically come about in about 5th grade, 6th grade, depending on curriculum. You're looking at that upper elementary, so we're kind of pushing into that a little bit. Interestingly enough, students usually do encounter fractions before they encounter negatives. There's a concrete picture of fractions in a little bit different way, and so those are usually taught at a little bit younger age, just so you know. But this has the idea that you're missing something, or that you've created something that you need more of, right? So it's a deficit in some way. So one of the things that I should probably make mention of, because your presentation on Wednesday, not that you're doing it, but that you're signing up for it, your goal as you create your sections of material is to create sections with context. You create problems with context, okay? I don't have a lot of context examples in here, but your book's got plenty of them, okay? I'm going to focus more on the strategies, the algorithms, those kinds of things, which is not what your presentation is supposed to be about per se. Okay, your presentation is about context. So keep that in mind. You should not just be modeling what you've done on yours off of what mine has done. It's a little different. So this is our first one in terms of algorithms, integer addition examples. So we're going to be taking a look at what's called the chip model. And this chip model, and the second one that says charged fields model, your book has now merged into one model, which is a good thing because they're really the same. All right, so just mark out charged fields. They don't have one called that in this book any longer. And we're going to look at the chip model. Okay, so we have 5 plus -3. And so what the chip model does is it creates chips, and a hollow chip represents a positive number, okay? I said that wrong. A hollow chip represents a negative number. A filled-in chip represents a positive number. They do that backwards of what other resources do as well. So we've got 5 solid chips. Okay, I want to erase things now because of how I'm doing this. That's okay. We're going to work with it. Okay, so this is the positive numbers for 5. All right. And then it represents negative chips as hollow numbers, not filled in. So they look like this. Okay, pretty good so far. All right, these chips are on kind of like a mat, if you will. They like to draw them in circles. So you're going to draw a circle around them as though it's like this is the playing field, right? Like if you're in the circle, you're part of the problem. Once you get kicked out of the circle, you're out of the problem. We're going to draw things with it, right? And what we see happen here, and for those of you who've seen this in proportional statistical, it's very similar, is we see things that occur that are canceling one another out. They're called zero pairs. So these two right here can cancel one another out and they can come out, right? Because they add to zero. And we can do the same thing with another pair here. And we'll do the third pair over here. And when we do that, and we're all said and done with everything at the end, we end up having that same mat, or whatever you want to call it, but it only now has 2 solid chips in it, and 2 solid chips represents the number 2. Okay, so your book actually uses some colors for these. So I'm going to mention 2 options. So solid and empty is one of the ways of doing this. Another way of doing this is, and let me just erase what I have so you can see another option. You don't need to erase, you can just make yourself a note. Another way in what they have done in this book now is that instead of doing them solid and dotted, or solid and empty, is they've drawn them as pluses. So you have 5 pluses and they're all in circles. So you're sort of representing the chips themselves by putting the sign of the value in them. And then they're doing the same thing with their 3 negatives, like this, and they're circling them and they're taking them out. Okay, so it's the same, right? It's exactly the same. And this with the pluses and the minuses is what they used to distinguish as a charged fields model. That's what I would have drawn, something similar to this, but without the circles around them on the one that I just had you mark out. But it's the same thing, right? And they use colors. I can't remember exactly the colors that they use. I think pink and yellow sounds right. And also, let me show you this. Nope, it's not in here. I'll bring it next time. We actually have chips that we can use that can do this too. So if you were really doing this with children, right, you would have, and I'll bring them next time, these chips. They look like poker chips. They're a little bit thinner and more plasticky feeling. And there's some that will have like, they color on different sides. Those are the ones that I wish we had. I think that would be fabulous. We don't have those. We just have red. I'm pretty sure we don't have those. Now that I'm saying that, maybe they are. We have red and we have yellow. Those are our colors. And so we have to decide which one's which. Usually we let red be negative because that's the color that shows up in lots of things associated with red. So red is negative, the yellow is positive. So we would have, in this case, if we were doing that this way, doing that way, you would have a circle and you would have 5 yellow chips. Oops, I meant to do this. 5 yellow chips. And you would have 3 red chips. And a yellow and a red combined together are a 0 pair, and they come out. Okay, so all of these images result in the same thing at the end. There's 2 chips that are left in there, and they're whatever you've called the positive chips. So as you're doing your homework, you're welcome to use pluses and minuses. As you're doing your homework, you're welcome to use colors, as long as you tell me what color is positive and what's negative, and then you can have freedom to choose what you'd like. So be creative, and you can use pink and purple if you want, right? Whatever, it doesn't really matter, but you need to distinguish between them, and you need to tell me which is which. Okay, so if you're going to use purple to represent positives, just say plus equals purple or something like that. Purple equals positive something. Okay, so this is called the chip model. Okay, it does a really nice thing of showing how things pair up in ways that they get out of the circle. And in all cases, we end up with 2 left. A number line model, this one's actually my favorite in this one. I tell you guys that sometimes, right? I like this one the best. I like this one the best because it blends really nicely into the things they've already seen with number lines and how they're still going to use number lines and graphs in the future. They're not going to use chips in the future. doesn't make them bad, it just makes them applicable to this one little tiny area, and number lines are applicable across a broader spectrum, okay? So that's why I like them. So the way that this works is you start with this number line, and you have a 0 on your number line. I'm gonna draw it first, and then I'm gonna show you how you can actually do this with kids in a classroom that's more hands-on, okay? So there's 0 in the middle, that's great. And the first thing says 5. So I'm gonna move 5 to the right. And I'm gonna label this as 5. And to show that I've moved 5 to the right, we're going to sort of draw an arrow that goes to the right 5. Easy enough. And then when it says plus -3, it means I'm going to add, but I'm going to add a negative, which means they go the other direction 3. So I'm going to actually move 3 back this way. And if you want to draw them like you're counting, like jumps or something like that, you can do that too. It doesn't have to be one big arrow. That would be okay. And where we end up is the number 2, and that's our answer to the question. So were I to do this in a classroom with children, what I would do is I would put a piece of tape on the ground. Okay? I'm going to do it with desks because we have them. So we're going to say this row that Madison in it is 0. Okay? And we're going to say that going to your right is positive because that fits with my picture, right? Positive is to the right. And then going left is negative. So we would have our child and we would say we're going to go 5 desks to the right, or we're going to take 5 steps to the right with the tape you have on the floor or whatever, right? So we're going to go 1, 2, 3, 4, and we're going to do 5. Okay, so we're all the way over here to Tessa. And then we're going to go 3 in the negative direction. So we're going to go 1, 2, and 3. Anna, do you remember what your row was called? It was 2. So we end up at 2, and if we had a tape on the floor, we would end up at 2 on the tape on the floor. Okay, so you can get up and you can move around. That's good news, right? But the number line picture actually corresponds to something that we use in the future. Okay, this next one is my least favorite one, but it does have good application for some of your special needs students who are the exceptionally bright ones, like the ones who are on the spectrum, but they're on the spectrum in a way that they just think in patterns. Okay, so I've worked with children like this before. You might have as well. So this is 5 plus -3, and here's how it works, okay? So you start with something that the child already knows from whole number addition, like 5 plus 2 equals 7. Okay, everybody good with that? And then you go, okay, well, what's 5 plus 1? And that would be 6. And 5 plus 0 would be 5. We established the pattern of what happens when we take the number 5 and we add something to it. Okay, are you with me? So when I'm looking at these numbers, then I'm going to take the next number and I'm going to go down 1, right? That's now going to be -1. But the pattern that I've established on the right-hand side just means it goes down 1 as well. It goes to 4. And then when I do my 5 plus my -2, it's the pattern. We're not really adding this. We're looking at the pattern. The pattern is 7, 6, 5, 4. Well, the next number is 3. And the one that we want here at the end, 5 plus -3, and in the pattern, it's the number 2. So we're thinking of things more in the perspective of how numbers interact with each other in patterns. Okay? So this one doesn't resonate with me, but that doesn't mean it wouldn't resonate with any of the kids in your classroom. So keep that in mind. You don't have to like it. That's not the goal. The goal is to teach kids what works for them, right? Okay. The other thing we're going to take a look at in this section that we haven't had to worry with before is absolute values. So absolute values are defined as follows. For any integer x, so this means you're looking at positives, negatives, or 0, right? Positive, negatives, or 0. If you take the absolute value of x, and x is positive, right? This means x is positive or 0. So if you take the absolute value of a positive number or of 0, it doesn't change. Absolute value 5 is 5. Absolute value 7 is 7. Absolute value 0 is 0. Doesn't change. Okay? That's what absolute value does. But if you have a negative number, this right here is telling you the sign changes. So, absolute value, let me give you an example. Absolute value of -5, you know what it is because you've worked with absolute values. It's 5, right? But I don't have any mathematical notation directly that says remove the negative, right? I mean, I need to do something that shows that I'm taking the negative off, but it has to be like a symbol that does that, right? So what we actually do to represent this instead is we write down that we're taking the opposite of -5. So this negative that's showing up here is actually coming into here, and it is exactly what is making this number change from negative to positive. Feels a little funny, but that's the mathematical notation we have to work with. Okay, it doesn't mean the number becomes negative. It means the number changes signs. And it was negative to start with, so now it's positive. Now, from a number line perspective, I think it's also worth noting what absolute values do, especially since I told you I like number lines. Absolute values are actually simply measuring the distance back to 0. So if we have 5, the absolute value of 5, let me do that again, is 5 because the distance back to 0 is 5. And if I had -5, the absolute value of -5 is 5 because the distance back to 0 is 5. Absolute values measure distance to 0, and that's why they're positive. Distance is a positive concept, right? If I ask you how far it is from here to home, you might have kind of a number of miles in your mind. You might not, but let's just say you do. I've got one. So distance from here to home for me is about 20 miles. About 20 miles to get to my house. But I wouldn't tell you it's 20 miles to get to my house and then tell you when I'm at my house it's -20 miles to get to Shawnee, right? Distance is a positive quantity. It's still 20 miles, no matter which direction I'm going. So absolute values are actually measuring that. Now, taking a look at how absolute values kind of work, we're going to classify these following statements as true or false. And what I'd like for you to do is first try them on your own without me explaining anything else, okay? And it tells you that if it's false, you need a counterexample. So remember, we talked about counterexamples before. It means an example that shows it's false. Okay? So take a minute, take a couple minutes, and go through the list and think, do I think this is true? Do I think this is false? And if it's false, how would I show this with a number example to a child? When you do get to a point where you've decided what you can decide, you've gotten to your ending spot, check with somebody nearby and see if you're thinking along the same lines. Okay, you guys ready to reconvene and see what you're thinking? Let's check our thoughts together. How about the first one? Do you think it's true or false? True. Now, it didn't ask us to justify why, but would you mind giving us your thoughts about why you think that's true, Kira?
Well, you can fill it in with different numbers, like 4 or 2 or something like that, and it's always going to equal the other one.
Okay, so she said you can fill it in with different numbers, like 4 or 2, and it's always going to work. We probably want to try not just positive numbers, though, but also try negative ones, right? And 0 as well. So that's a good way to check and see if something works. Try some numbers. And in particular, since we're dealing with absolute values, checking something positive and making sure you check something negative as well, really important. Okay? From a general standpoint, the reason that this works is because when you raise something, or when you do an x to the 4th, let's do that one, you're multiplying it together 4 times, right? Okay? If you have positive numbers and you multiply positive numbers, you get positive numbers, right? That's closure for multiplication that we looked at in whole numbers. But what happens when you multiply negative numbers? We haven't actually looked at properties of negative numbers, but what does happen when you multiply 2 negative numbers together?
Positive.
You get a positive. So 2 of them grouped together are going to become a positive, and the other 2, I put too many of them there, didn't I? Sorry. The other 2 that are grouped together here would become a positive. So because I can put them in pairs, because x to the 4th has 4 of them, they're able to multiply in pairs and become positives. So what ends up happening is this x to the 4th inside here is always positive. Do you agree? No matter what kind of number I put into x to the power of 4 is going to be positive. So what that means from this definition is that I'm in this case right here. This case says if I have a positive number for x, which we do because it's called x to the 4th right now, all I have to do is lift the absolute values off of it and it's going to be the correct value. And that's what we see happening on this problem. Does that make sense? How is that different from b? Is b true or false? It is false. Allie, do you have an example? But you have a specific example first. But that's exactly the reason why. Somebody give me a number example that can show why this doesn't work.
-2.
-2. So let's try -2. Okay, so this is what putting it into the left-hand side would look like. So I have -2 times -2 times -2 times -2 times -2. There's 5 of them, right? And they're all inside this absolute value. And what Allie said is correct. From what we were looking at last time, we're going to pair them up. So these 2 get paired up, and they're going to become positive. Now, it happens to be positive 4, so I'll write down positive 4, but the point really is that it's positive. And when these 2 get paired up, they also become positive, right? These are still multiplied together. But this -2 at the end stays negative. So when I multiply across here now, I've got potentially a bunch of positives. I could even have more of them if I had a bigger odd power here. But I've got some positives here, 2 of them, and then I've got one single negative, which means the whole thing's going to be negative, right? So this value inside here could be negative. Could it be positive?
Yeah.
Sure. We just would need a different value for x to show that, right? Let x be 7 and we could do it. Right? Let x be positive 2 and we could do that. So you can't prove something's true by an example. You can sort of develop an intuition and feel like I'm pretty sure, right? But you can definitely prove something's false by an example. All you got to do is give one example where it doesn't work. So what happens is, because this is a negative, or could be a negative inside, we could be, let me clean that up. Get the right one. We could be in this case down here, right? We could be in the case that the x value is negative, in which case I don't just lift the absolute values off like that part B problem said. I actually have to change the signs. And changing the signs means putting in an additional negative to what was already there, right? So if I put in an additional negative to what was already there here, that will change the signs. So imagine over here, now we'll use the example that we've already been working with our 2's. I have 4 times -2. What is that?
4 times 4 is 16 times -2 is
-32, right? And what the B part, if you will, or the second part of this absolute value definition says I'm going to do is I'm going to take a negative and put an additional negative in front of my negative 32. And in doing so, that becomes a positive 32, correct? But you have to notice that the number in here and the number in here are not the same number. And that's what it actually set up having to be able to do here. It'd be the same thing inside as it have it outside. And it isn't, it's something with the opposite sign. So this would be a false statement. C and D sound very similar. C says absolute value of x is not negative. Is that true? Yeah, that is true. And we had a problem, like the definition itself showed that. If we talk about it from the perspective of it being distances, that makes sense. The shortest distance you can go is to not go anywhere, it's 0. You can't talk about negative distances, so this works. But is absolute value of x positive?
No. False.
So if it's false, here there is also a chance. Why or how could this be false when the one right above it was true? Anybody see the nuance to what's being said? What do you think, Riley? If x is 0, whoops. If x is 0, I have the absolute value of 0. And that's in that first definition, right? The first part of the definition. I just remove the absolute values. It becomes 0. The 0 is not a positive number. It's not a negative number either, but it's not a positive number. So this is a really good example of it. All you need is one example to show something's false. And in fact, this is the only example that will show it's false. You don't have a whole bunch of options. You have one. Okay? Does that make sense? All right. Let's take a look then at properties of integers because they sort of kind of came up in the middle of that problem. Closure, do y'all remember? Do you have a question, Madison?
No, I was just processing in my head.
Okay.
I'm good.
You're
now.
good. Okay, fabulous. Closure. What does closure mean? We've talked about it now, right? Do you remember? Nobody likes the closure one. Closure says that if you have integers, in this case it's integers because we're working with them, and you add them together, what will you get? You'll get an integer, right? If you add two integers together, you get an integer. That is the closure property for addition. The next one is the commutative property for addition. What is commutative?
You can switch them around the source.
Yeah, the order changes, right? It's where we get the word commute when you talk about your commute to work, right? The order of your locations changing, right? So it's telling you that A plus B and B plus A are the same. Associative requires all three of the A, B, and C, right? And it talks about how we associate our integers together. So if I add A and B and C where I group the A and the B together first, that's the same thing that'll happen is if I add A, B, and C, but I group the B and the C together first. How I associate them, how I group them doesn't change the value of the problem. And sometimes it's much nicer to add two things together in one location than the other. It adds to 10 or something like that. It adds to something nicer. So it's more friendly to do that. Identity. What do you think the identity is for addition of integers?
0.
0. You guys agree? Identity means something you add to it and it doesn't change it. So if we add the number 0, whether it's on the left or the right, the value changes. And we say then that 0 is the additive identity. Okay, so here's what we're going to do. The next two examples are going to take no time at all. We're going to do them, but we're going to table our discussion until Wednesday to do the group work, and we will start 5.2. Stay tuned for 5.2 though, because I'm going to post new notes because there's definitely something that's missing from the notes currently. Okay, y'all good? Here's our two examples. Oh, I'm sorry. Did I switch 2 pages? I did. I take it back. We're going to continue our discussion next time for sure, and the group work, but I skipped too many pages. Let me do this. Let me do these next two theorems. That'll work just fine, and then we'll stop with subtraction. The additive inverse property says the following. There's a negative of every number. There's an opposite. We call it the additive inverse. And when we add it to the original number, we get back 0. Right? And you guys have seen this, right? This is 3 plus negative 3. It's going to give you 0. Or if you start with a negative, right? Negative 4 plus positive 4, you get back 0. So additive inverses are simply the same value with the opposite sign. How do you know they're additive inverses? Because when you add them together, you get 0, right? That's the property. The property is not I added a negative or I took off a negative. The property is when I added them together, I get 0. And we'll just stop right there. It's fine. We'll start with theorem 5.3 next time.